strings and pulleys. First of all, let's talk about what strings and pulleys do. Strings, ropes, cords, oops, let's spell that right, cords, chains, anything like that. Vines, chains, you can imagine anything that's sort of rope-like, right? They all have something in common. When you apply a force to a string or a rope or a vine or a chain, you create tension in the rope. And tension is just another word for force. So tension can be used anywhere you would use a force in any of your equations. It is a force. We just happen to call it a tension because it's sort of a specialized force in things. Now, anything can have tension, right? It doesn't have to be a chain or a vine. You can have tension in your arm. You can have tension in a concrete block or a tree. But typically, it's all strings and ropes and vines and chains. Okay. Now, an interesting thing about tension that we have to point out is this. If you have a little tree here and grass, and you put a rope around the tree, and then you grab the other end of that rope and you pull on it really hard as you can, you're applying a force to the rope, and that force that you apply results in a tension in the rope. But the problem with tension, or the confusing thing about tension, is that the direction of the tension, because remember, force is a vector, the direction of the tension is a little bit confusing, because this rope is pulling on the tree in this direction, but it's also pulling on the man in this direction. So tension pulls in all directions. Tension pulls in both directions. And of course, tension never pushes. Ropes can't push things very well, can they? So tension is a pulling force that is in both directions in a rope. So if you have a tension force, it's going to pull in both directions, which means that you have to kind of infer the direction from the context. And so often, when we calculate tension, what we're really thinking about is the magnitude of the tension only. How much is it? So the magnitude is what we care about. And then we can infer the direction from the context in which the rope or chain is involved. Infer the direction from the context, realizing that it could be either way, right? From the tree's perspective, this tension would be a positive tension to the right. But from the perspective of the man, the tension is to the left, so it's a negative. Then it can be both. So that's what I wanted to tell you about tension, first of all. And then, the other thing we should talk about are what pulleys do. Pulleys are basically devices. Pulleys are devices that change the direction. Change the direction of a force in a rope, or a vine, or a chain, or whatever. I'll put a rope in quotes. Any kind of rope-like thing. So, if you have a rope this way, and you put a pulley, a little round wheel, and you wrap the rope around it and attach it to an object, you can change the direction of your force. If you pull this way on the rope, that's a downward force. The pulley changes the direction to a sideways force on the block. So they're convenient devices for changing the direction of force. They can also be used to reduce the amount of force as a simple machine, but for this particular lesson that we're trying to get our heads around, we're not actually trying to do that. We're just turning the force direction, changing the direction of the force. So we're not trying to actually reduce the amount of force. Okay, so let's do a simple example of a string and a pulley question to see how it might work. Let's take a tabletop, and we'll put a block on top of the table, and we'll say that this block has a mass of 6 kilograms. And then we'll put a pulley right here on the edge of the table, and we'll tie a string to it, and we'll swing the string down around the pulley, and we'll hang from the pulley and the string another block of 8 kilograms. And see what happens. Now what we'll do first is we'll consider a situation where there is no friction, just to keep it simple and get our heads around the reference frame idea. If we draw in the forces, free body diagram, we would have a force of gravity pulling down the 8 kilogram box, which I'll call FG8. And we could figure that force out if we wanted to, because we know it's mg, so it would be 8 times 9.8, right? 8 8s are 64, 72 for that, 78.4, I believe is what that would be. Newtons of force. There's also a force of gravity pulling on the 6 kilogram block over here. So we can figure that out. I'll just write that here. Fg6 is mg. And we can figure that out. 6 times 9.8. 6 are 48. 59, I believe, is that what that would be. Right? 58, sorry. 58, that's right. 58.8 newtons. Now we also know that since the 6 kilogram block is sitting on a surface and it's not falling downwards, that surface must be pushing upwards with a normal force as well. So we'll put the normal force there. And in fact, if we know anything about forces and Newton's laws, we can pretty much infer that that normal force is going to have to match that downward gravity force of 58.8, isn't it? Well, we'll talk about that in a minute. Now, the only other force that we would have to worry about then is the tension forces. Inside this string, there would be little tension forces. One would be pulling this way on the 6 kilogram block, but on the 8 kilogram block, it's kind of pulling up this way. Tension always pulls, it can't push. You can't have this rope pushing downward on a block, it just doesn't work. If you ever tried to push something with a rope, you probably were not too successful, right? So you see how the tension has two opposite sort of directions. So how do we deal with this? In order to do the directions, do we do plus for left or plus for right and minus and up and down? The whole thing doesn't seem to fit. What we have to realize is that if we look at this picture, we can tell that very likely this 8 kilogram block is going to pull the 6 kilogram block off the table, isn't it? Especially without any friction. Which means that the blocks are going to move sort of in this direction. This is the way everything will go and tumble off the side. And that happens to be a direction that we call clockwise. It's the same direction that the hands on a clock turn, clockwise. And so what we will do is we will use a reference frame. Our reference frame will be to consider anything that causes a sort of clockwise motion, or anything that's in the clockwise direction will be considered to be a positive number. And then anything that we consider in the other direction, which would be counterclockwise, we will consider that to be negative numbers. So right away we notice some weird stuff. This 784 newtons, before this video we might have said it should be negative because it's down. But if you look at the clockwise direction, in our new reference frame of clockwise, this is a positive force, isn't it? Because it is in the clockwise direction. However, if you look at this little tension here that's pulling on the 8 kilogram block, it's pulling in what we would call the counterclockwise direction. So it would be represented by a negative force. So basically, in this picture, we could also say that clockwise is right and downish. Those two directions are plus, positive. And counterclockwise is kind of up and left. Those two directions would show up as negative. Once you get your head around that, the rest of this is really not that difficult at all. So, let's take an actual question. Well, we may as well use what we've already got. Let's say that we started off with this question with the 6 kilogram and 8 kilogram block. And the question we were after is, what exactly is the tension in the rope? How much force is there in there? That would be our goal. So how will we figure this out? Well, there's kind of two sort of steps. The first thing we do is we analyze or we consider, I'll put number 1 here, consider the motion of the entire system. The entire system. So what does the entire system look like? I'm just going to resketch the picture really quickly here. I'm not sure why that one's there. We go. Here's the 6 kilogram block, and then down here we have the 8 kilogram block. That is where we are. A little pulley there that's allowing the rope to bend for us. Well, the whole system is going to move together. If you think about it, because these blocks are tied together by a rope, they have to move the same way. The rope is not stretchy, it's not elastic, we assume that. So whatever the 8 kilogram block does, the 6 kilogram block is going to do it too, because they're tied together. So the system, the entire system, is considering the entire 14 kilograms as if it was one big block moving all together. Now at first that seems odd because it's clearly 2 blocks with a rope between it. But I want you to consider this. Consider looking at one single block. This is kind of an aside, but think about one single block. If you pull on the block, you think, oh, well, it moves all together because it's one block. But it's not really one block, is it? If you shrink down on the magic school bus, you would notice that it's made up of little molecules. And each of these molecules is not connected to each other physically. But there are tiny little forces of attraction between these molecules that are like little strings. And so if you pull on one of the molecules, then your pull is transferred through all the little strings and it pulls all of the little molecules along and the whole box moves. So in reality, nothing is just a single block. Everything is tiny little blocks attached by strings. And yet all of these move together as one. And that's the same thing as what we have here, except it's on the macroscopic level. Instead of molecules, we have 2 big blocks attached by a string, but they will all move together as one. So, the entire 14 kilogram system. So let's look at the motion of the entire system. To do that, we'll put our little forces back on. We said force of gravity here, force of gravity, and that was mg, right? So it was 8 times 9.8, and I believe 78.4. Right, the 8s are 64. And then we had over here a gravity force, and it was 6 times 9.8, so 6 8s are 48, 58.8. And we said there would be a normal force sticking up here, stick it in there nice and small. There was no friction in this question, we had said, right? So no friction. I'm not sure if we wrote that down or not, but remind yourself there's no friction involved, so we don't have to worry about that. Which basically means the normal force isn't really going to matter, is it? Because the normal force is what's used for friction. Now, when we were looking at pulling the little molecules, if you pulled this with a force, Newton's law was F equals ma, right? Did you worry about the fact that there were all these tiny little strings inside with tensions in them? These tiny forces between... No, you didn't worry about those because they were inside the block and they don't really matter. We pull on the block, they all do their thing, and the entire block will accelerate. And the same is true here. When we consider the entire system, we don't have to worry about this string at all, because it's inside the system, just like these little things are. Whatever we do to the 8 kilogram block, we just know it'll automatically happen to the 6. And so we're not even going to consider the tension inside the rope when we consider the whole system. So, let's do it. F net. Now, if we look at the F net on this sort of thing, we can tell right away that the gravity force on here is balanced by the normal force. If we did a little F net y equation, we would see that there is no up and down motion or acceleration, and those two would equal and cancel out. So these two forces are not going to contribute to our clockwise or counterclockwise motion, are they? They're not even going to be in the picture for this simple question. The only reason we would use them is if there was friction involved, and we'll do that example after we get the hang of it. So, the F net then is one force only. It's the Fg on the 8 kilogram block. It's the only thing that's causing this to move in our clockwise or counterclockwise direction. We can be pretty sure that this setup is going to move clockwise. Eh? Okay, well MA is F net, just like it was before, and we figured out this mg 784. Now I'm using a positive number. I know it looks like negative down, but we are using a reference frame where clockwise is positive. So this is actually positive in this particular reference frame, right? And then mass, we want to know what's happening to the entire system, so we get this. And if you divide by 14 on both sides, so you can have that number, 78.4 divided by 14 is about 5.6. So the entire system would be accelerating at 5.6 meters per second. That means that it would be moving in a clockwise way around like this, but accelerating as it went at 5.6 meters per second squared. So every second, it's going 5.6 meters per second faster. Right? Okay, that's not the tension in the rope. We were after the tension in the rope. Well, to get the tension in the rope, what we can do is look inside, and we have two options. We can pick either the 8 kilogram block or the 6 kilogram block. And I'll do them both so you can see that they actually work out to the same number. Let's look at just the 8 kilogram block. Here it is, floating. Let's look at the forces that are on the 8 kilogram block. We said there was a force of gravity. And we already figured that out, 78.4. So we know that. What other force is acting on the 8 kilogram block? Well, now we have to consider the tensions in these ropes, or in this rope. There's a tension that would be pulling this way from the rope on the 8 kilogram block, so I'll put it in and I'll call it tension T. Remember, tension is just a force. And that's all there is on the 8 kilogram block. That's its life in a nutshell. So if we write a net force equation, F net, and we're talking only about the 8 kilogram block now, so we're not talking about the whole system. We write over here, there's tension, and there's this force of gravity that's on it, on the 8 kilogram block. Maybe we should have put an 8 here to keep our gravity straight. Well, that's going to cause an acceleration, ma. And this is our mg over here. And we know that this mass is 8 kilograms, but we know the acceleration it has to have because we figured out that the entire system has this acceleration, which means every part of the system has this acceleration, right? So this acceleration is going to come over here, and it's going to go right over there where that a is, and I'm going to write 5.6 in there. So that's the reason why we did that first step. And we have tension again, which is our goal. This is the guy we're after. And here we have 78.4. And again, I'm using positive because it is in my clockwise direction. You have to remember that reference frame. If you multiply this, 6 8s are 48, and 5 8s are 40, so this looks like 48.8. Right? And then you can see what's going to happen. Now, the acceleration is also positive because it was also in the clockwise direction, wasn't it?
44.8, sir.
44.8? Thanks for that. Let's fix that up. 44.8. All right. Then we have 44.8, and we have to move this 78 over here and subtract it to get the tension. And so when you subtract those, it comes out to what?
33.6.
33.6. And not just 33.6, but negative, right?
Yeah.
33.6 newtons equals the tension. Now, why would the tension be negative? Well, in our reference frame, this upward direction would be making counterclockwise motion. So we would very much expect that the tension should work out to a negative number. But technically, when we calculate tension, we only consider ourselves with the magnitude. So the correct answer could easily just be 33.6 newtons. The negative just means the direction in this case. Now, what if we had decided instead to look at the other block by itself instead of this one, which is another option that you can do. So let's go to the other block for a second and remind ourselves what it looks like. It's a 6 kilogram block sitting on the surface, and it has a little tension that's pulling this way, to the right. So that would be the T in the case of the 6 kilogram block. So we could do this all again very quickly for the 6 kilogram block, but we should find out that it's exactly the same. So here it is, 6 kilograms. We have a force of gravity this way, which we said doesn't really matter in this case because, first of all, it's balanced by the normal and it's not contributing to any motion clockwise or counterclockwise. And there's no friction, so we just kind of ignored those. Now, we have a force of a tension pulling this way. It's from the other picture, that purple arrow. And because there's no friction, there's nothing pulling backwards, that seems to be the only force that's pulling on this block. And so if we do our net force equation, the net force in our clockwise, counterclockwise direction, reference frame, is simply the tension that's pulling on this block. And so F net is MA equals T, but this is a mass of 6 times 5.6. That was the acceleration that we found. Both blocks have the same acceleration, then you'll notice that the answer comes out to 32.6. But this time it came out to a positive number, didn't it? Because in this situation, this is a clockwise tension, and so it came out to a positive number. So it doesn't matter which one you do. And the answer, the best answer that I would give if they were asking for the tension is I would just consider what we call the magnitude, right? The absolute value is the mathematical way of finding the magnitude. So the answer is 33.6 newtons of tension. And we would know that it could pull both in the positive or the negative direction. Yeah.
Why do we disregard FG?
Why did we disregard FG? That's a great question. Because this arrow pulling down, you're talking about this one, right, on the 6 kilogram block? It has no way of moving the block in the clockwise or counterclockwise direction. And so the only time we'll need that is if we need FG to find Fn to find friction, which will be the next video. We'll do an example with friction. But for now, we're just trying to get our heads around this clockwise, counterclockwise reference frame. Okay? But we did count the gravity on the other block, obviously, because it was the one that was making motion in the clockwise direction. All right, that's the end of that.